Okay, so homework 3 due tonight. So far, so good? Okay, iffy? Any questions? Okay, yes. Who wants to go first? Go ahead.
I want to ask about stability.
Yeah.
You gave us some examples of proving stability.
Sure.
Where there was I forget what it was, but if that criteria is not met but it looks stable, is there a way to say that other than it can't move without deformation?
Yeah. So if essentially what you're doing is you're looking for red flags for instability, right? So there's not really a specific test or sign for stability without doing a full-blown analysis. If you can rule out, okay, it's determinate or indeterminate, so it doesn't have more equations it doesn't have more equations than reactions, right? So if it doesn't have more equations than reactions, it's determinate or indeterminate. So you've ruled out one red flag for instability, but there's others to check, right? You've got the geometric instability, you've got we looked at a couple of those where, if all of the reaction lines intersect at a point, then it can't resist rotation. So you're ruling out instability flags, right? If you can do that, and then, you don't have anything else to think about, then it's totally fine to just say it's stable, it can't move out deformation, there are no red flags for instability, something along those lines. Yeah.
For the second problem on the homework,
Yeah.
when you talk about not doing it in X and Y, are you treating it, or
The truss, yeah.
yeah, the truss are you treating it like if it were in dynamics when we had a box on the ramp problem, we flip the coordinate system like that? Is
Yes.
that what you mean by?
Absolutely. Yep, that's exactly the thing. Let's see. I have that. Here we go. Yeah, exactly. So this is right along those lines where you can choose your coordinate system, right? So you can align your X and Y like that if it's convenient for the truss, right? Another comment on this one, remember that the method of sections is great for when you don't need to find all the forces, right? Method of joints, what is method of joints? It's really just the method of sections that isolates every single joint when you go through it one by one. So using method of sections, you don't have to make cuts that are straight lines or anything like that, right? You can make cuts that isolate joints. So you can cherry pick joints out of the truss and analyze the ones that you want, right? So keep that in mind. That can be helpful as well. Okay. Any other questions? Okay. Good deal. We do have office hours today. Myself and Mohammed both have office hours today. So if you do think of anything before homework is due, try to get that answered during office hours, and we will do our best. All right. So today we're going to wrap up our conversation regarding shear moment elastic curve, and then, time permitting, start talking about finite element analysis. So last time we looked at this example of shear moment on a frame, and we went through and drew all the shear moment diagrams for the columns and beam of this frame. And so remember I talked about how my approach was to, after finding the reaction forces and breaking the frame apart at the joints, I started with the two columns, right, and found the forces at joints B and C just using the columns. Then just transferred those forces to the beam to draw the shear and moment diagrams. Now, if you had done that and maybe find that the shear or moment diagram doesn't close, then that's a sign that you maybe got something wrong with those joint forces, all right? Or maybe you missed something in the transfer because remember, it's equal magnitude, opposite direction whenever you transfer forces from one joint to the next or from one side of a cut to the other. And, alternatively, you could have marched through the frame, right? You could have found the forces at joint B, transferred those forces to the beam. So now those forces would be known, but these would be unknown. And then you could apply equilibrium to the beam to find the forces at C and then just transferred them to the column. So, a couple different ways you could go about solving that. Either way, you should always end up with the same results. And a few other things I want to note here, all right? So this is kind of on the next page. So on the next page, we have the same frame, right? This is the expanded free body diagram showing all of the forces and reactions with their correct magnitudes and directions. And so note that at every joint, the sum of moments is equal to 0. So you have, right, at joint C, 200 kip feet counterclockwise on the beam and 200 kip feet clockwise on the column. At joint B, you have 1,000 kip feet, 1,000 kip feet, right? Again, opposite directions on beam and column. Now, one interesting thing to point out about that, look at the moment diagrams for those elements, right? So over here at joint B, you have a counterclockwise moment on the column, which is a positive moment, right, according to our sign convention for the top of a column. And then a clockwise moment at the left end of a beam is also is also positive, right? So we have positive 1,000 at the column and at the beam at point B. However, over here at joint C, right, we have a counterclockwise moment on the beam, which is positive for the right end of a beam, all right? And we have a, this is actually clockwise, right? So my note, right? We have a clockwise moment at the top of a column, which is negative for the top of a column. So just because a moment is positive or negative at the top of a column doesn't mean it's going to be positive or negative at the top of the beam. It depends, or at the end of the beam, right? It depends on whether you're looking at the right end or the left end of the beam, according to our sign convention, because, all right, this was our positive moment for beam, and this is our positive for column. So that's just something to keep in mind. However, they will always be equal magnitude, opposite direction. All right, so then this note at the bottom of the page, all right, if we have more than 2 members that connect at a rigid joint, then there's really no unique relationship between shear values at the ends, because shear and axial will just kind of work their way through. So, but we do still have the rule that sum of moments at that joint is equal to 0, okay? So there's 2 different ways we can think about this, all right? So over here on the right, we're really looking at the expanded free body diagram of frame members at a joint. So the moments that are shown here are the end moments of members. So a joint, all right, would be located in the middle there. And then if we wanted to blow that joint up, right, it would look like this. So over here then, right, we have the same moments just applied in the opposite direction at that joint. And so here you have like the rigid joint, right, that maintains 90 degrees. And another way to think about writing the equation sum of moments is equal to 0, right, is shown here. You can also think about that as the sum of the counterclockwise moments is equal to the sum of the clockwise moments, right? So that's the same thing. So just a couple comments there to help you keep track of all of these things, right? All right, questions? Okay. All right, so now we're going to talk about elastic curve, which is one of my favorite topics in this class because it's kind of fun to draw the elastic curve. You are familiar with the elastic curve from mechanics of materials when you derive the equation for this. It's that lowercase v of x, where sometimes you start with the moment equation and you integrate twice to get that, and sometimes you start with the load equation and integrate 4 times to get that equation. Good news is, in this class, we're not going to be doing that integrations. We're not going to be deriving those equations. We're going to be applying more of an intuitive approach to drawing the shape of the elastic curve. So we're going to go through a few definitions and rules and then start applying it to examples to show you what we're going to do. All right, so the deflection curve of the longitudinal axis of a member subject to bending is the definition of elastic curve. Longitudinal axis is what I want to write here of a member. And I often abbreviate this as just EC for short. Now, the cool thing is that the curvature of the elastic curve is directly tied to the moment diagram, right? And this makes sense, right? If you think about how you get to that equation, right? You get through, it's a second integration from the moment equation, right? So it's connected there. And another way to see this connection is through what we already know intuitively about bending, right? So we've talked about how positive moment is one that makes the beam smile, so you have tension at the bottom and compression at the top, and a negative moment results in the frown. So for a positive moment, we know that the elastic curve is concave upward. And for a negative moment, the elastic curve is concave downward. And then what about where the moment is equal to 0? Well, there are 2 different possibilities, or 2 different types of situations where moment is equal to 0. If it's just crossing the x-axis, then that's just a change in curvature, right? So it's either changing from concave up to concave down, or it's changing from concave down to concave up. So we call that a point of inflection. So that's an inflection point of the elastic curve. And we'll abbreviate that as IP, or sometimes it's also noted as POI. And then a few other comments on that. All right, so I'll just write down what I said. So the beam curvature changes sign at an inflection point. And now, if the inflection point is at a hinge, all right, and we know that moment has to be equal to 0 at a hinge, right? We defined that with the behavior of a hinge. Then the slope of the elastic curve will be discontinuous. We'll look at examples where that's the case. All right, so that's sort of one category of moment being equal to 0, if it's just crossing the x-axis or if it kind of touches the x-axis and then stays positive or negative above and below. Sometimes that happens too. So the other scenario is if moment is constantly 0 for a segment of the beam. If that's the case, then there is no curvature for that portion of the beam. So the deflected shape of that segment will be linear. All right, so if there is no moment, there is no beam bending at that point, right? So it follows that there shouldn't be any curvature and the beam deflection will be linear. All right, so when drawing the elastic curve, it's really important that you always make sure to account for the support conditions. All right, so we'll do a couple of very basic examples right here. If we have a simple beam with an overhang and a point load between the supports, our moment diagram, right, will look something like this. Not curved. All right, so our moment diagram will look something like that. And the elastic curve, when we draw that, all right, I always like to sketch the location of the supports on the elastic curve diagram because that's a good reminder of what the deflected shape needs to do at that point, okay? So with a pin support and a roller support, that beam, the slope can change, right? So you can have a non-zero slope there, but the deflection has to be tied to the support, right? So you can't displace up or down there. So for this, we have the first segment here where you have positive moment, all right? So the beam will be concave up. And then from this point on, we have moment is equal to 0, right? Because it's, or because the moment is equal to 0 there, right? The elastic curve will be linear at that point. So the deflected shape then, right? We have to have 0 displacement at the supports, concave up, and then linear beyond that. All right, something like that there. So these, of course, are very exaggerated deflected shapes. On the right side, we have a cantilever beam with a point load at the free end. Moment diagram will look like this. All right, so we have negative moment for the whole thing. At the fixed end, right, we can't have a slope, right? We can't have displacement either. So no rotation, no displacement, and it has to be concave down. The only way for that to work is for it to deflect downward. All right, so these are obviously very simple examples. You could have drawn these deflected shapes without looking at the moment diagram, but it's just a first step towards connecting the two. So I'll just note here for pin support or a roller. The value of the elastic curve is equal to 0, but the slope is not equal to 0. And then here for a fixed support, we have the value and slope of the elastic curve has to be equal to 0 at that fixed support. Okay. All right, so now we'll do some more interesting examples. Here we have a simple beam with an overhang and some loading applied. Moment diagram is given. All right, so moment diagram from A to B would be quadratic, right? Because the load is uniform. And from BC, that moment diagram would be cubic, since we have a linearly increasing load. So the important thing for the elastic curve is to identify where along the length of the beam moment is positive, where it's 0, where it's negative, and then also where are the supports. So looking at the moment diagram, all right, we have this region where moment is positive. That tells us that the elastic curve will be concave up for that entire stretch. And then where we have negative moment, the elastic curve will be concave down for that whole segment, right? We also have a pin support at A and a roller support over here at B, which coincides with the largest negative moment value, right? And so we can go ahead and sketch the deflected shape with that information. We know it has to be 0 at the supports. And then for concave up, to start off, it has to deflect downward in order to be concave up and maintain the support condition at A. At this dashed line where the moment changes from positive to negative, the elastic curve will change from concave up to concave down. It does not mean that the elastic curve value has to be 0, right? In fact, it's usually not the case. Sometimes that may happen, but moment being 0 does not equate to elastic curve being 0 in general. All right, so we'll draw this, all right, concave up, and then here it's going to switch to concave down for the whole rest of the beam. So this point right here is your inflection point. That's where it's changing from positive curvature to negative curvature, and it can be a little tricky to draw it perfectly. All right, so I'll usually just ask you to identify the inflection points and do your very best to draw it concave down on one side, concave up on the other as appropriate. It's also going to be a smooth, continuous line even through that inflection point. And by the way, if you want some practice on drawing shear and moment diagrams, this same beam I believe, and the next one as well, are on D2L as practice problems for drawing shear and moment diagrams. So feel free to check that out if you want. All right, questions so far? Okay. All right, next example here. Got our beam with the hinge this time, all right? So we have pin, roller, roller, hinge, moment diagram as shown. We will draw the elastic curve. So I'm gonna start with drawing in the location of the supports on the elastic curve diagram. And then I also like to note if there is a hinge on the beam, I also like to sketch that on the elastic curve as well as a reminder. So that's one of the locations where a moment is equal to 0, right? So that's one thing to always check. Moment should always be 0 at the hinge. And then the other location where moment is 0 is over here. So that will be our other inflection point. So this first region, we're going to have positive moment. So we know that beam will be concave up. And then in the middle portion, we have negative moment. So the beam will be concave down. And then in the last segment, we have positive moment. So the beam will be concave up. I'm going to go ahead and label the elastic curve diagram there. All right, so noting that it has to be 0 at the location of the supports, but since these supports are all pins and rollers, we can have rotation at those points. So the first inflection point is the hinge. At the hinge, the elastic curve will have discontinuous slope. So I'm going to draw it very exaggerated, but show you what I mean. So we start off concave up. All right, so it could look something like that. And then at the hinge, all right, discontinuous slope. So it can be kind of a sharp change to concave down instead of a smooth curve like we drew on the last example. And then here, all right, it stays concave down until we get to this point where it's going to shift to concave up. So this is our next inflection point. Questions?
Are you too worried about like drawing those to scale? Like the
No. Yeah, don't worry about drawing them to scale. I'm going to be just looking for, are you meeting the support conditions correctly? Are you showing the correct concave up or concave down? Are you identifying the inflection points correctly? And then, right, the locations where, well, that would be redundant with support conditions, right? So, yeah, so those are the three main things I'm going to be looking for. Yeah, don't worry about magnitude. All right, we're just doing qualitative stuff with elastic curve. And go ahead and draw them exaggerated because that's usually the easiest way to get all the information out there clearly. All right, so next, I'm going to have you practice. All right, so here's an example of a beam with two hinges. This shows the process of just finding all the reaction forces, and then the shear diagram is drawn here. So here's my first challenge to you. Based on, see if you can just draw the shape of the moment diagram. Don't worry about values, right? to a certain extent, right? In order to, you'll have to do a little bit of math in your head to get like some of the zero locations correct on the moment diagram. So try to get the positive and negative and zero magnitudes correct on the moment diagram, but mainly just focus on those components of the shape, right? And as you're doing this, remember that I kind of, blew through the introduction of this beam pretty quickly, but the hinge locations are at the two ends of the distributed load. Right, that's where the hinges are located. And if you got the moment diagram down, go ahead and start drawing the elastic curve. And don't forget about the supports. You might need to look at the previous page to remember what they are and where they are. I guess for those of you that don't have the previous page in front of you, I'll go ahead and sketch them on here for you. So got a roller here, a pin at B, here are your hinges, there's a roller at E, and another roller at F. All right. I think some folks are through, some are still working. So there's a few other things I want to get through today, so we'll just move on for now. But you can see the solution on D2L, all right, the full solution. But here's your moment diagram shape, right off the bat. Based on the hinge locations, you know it's got to be 0 there. It's quadratic in between, and then linear portions before and after. So you can get something like this. And a quick verification, right? Your linear portions, you have -6 times 8 to get you down here, and then +8 times 6 to get you back to 0. So the math checks out there. All right, any questions? All right. So just a few comments on homework 4, which will be due next Monday. First problem is a cable problem, and this is an open-ended cable problem. So I did add a hint to it shortly after I first posted this, so if you were one of the first people to download it on Friday, maybe just check to see if it has this hint in there. If not, go get the new version. So what that means is that there's more than one solution to this problem. And you're going to have to make some assumptions in order to get through it. So this is sort of getting a taste of design and, training your brain to think creatively and critically about the problem and what you can manipulate with regards to the geometry, right? What assumptions can you make that don't violate any of the laws that we've gone through with regards to statics and what you know about cables and cable tensions. So think about that. And then you've got a beam where you're asked to draw shear and moment diagrams and elastic curve. So this is just a long, continuous beam with a couple hinges, fixed support at the left end, and some rollers along the way. The textbook problem is, if I remember correctly, this is a problem where you are given the moment diagram and you are asked to draw the shear diagram and also the elastic curve. And then for the frame problem, all right, you're given all these loads, draw the shear and moment diagrams for this frame. And then if you want some extra credit, take a stab at sketching the deflected shape of that frame based on what we have discussed regarding elastic curve, right? Because you'll have the moment diagram, so you can use that information. And then also remember what we know regarding rigid joints and pinned joints and how they behave differently, okay? Any questions?
On the elastic curve of the entire thing or just individual members?
The whole frame, yeah. So draw the deflected shape of the whole frame as the whole frame, yeah, for full credit anyway. All right, so up through this topic, elastic curve, this is the last topic on exam 1, which is coming up next Friday. So anything beyond this will not be included. All right, we've got coming up, right? I talked about that. So lectures 1 through 11. So next we'll be talking about finite element analysis. And I am going to go ahead and start that topic today just because the intro is a little bit long, and so I want to get a little bit started on that so that we don't fall behind in those finite element lectures. So we may get through the first page, and if we do, cool. If not, we'll at least get some of the basics out of the way. So the finite element approach, all right, the textbook sections that I've assigned for reading on this subject are, to begin with, just 19.1 and 19.2. So those are just some short sections to read that will introduce this topic. The idea behind this method and why we teach it is so that you'll have the tools to use matrix methods to analyze certain types of two-dimensional problems. And this is the approach that is essentially taken for finite element programs. So the programs that you will use to actually analyze these types of problems in the real world use this method behind the scenes. And so sometimes, it depends on the program, but some of those programs allow you to get back into their matrices and actually manipulate them. And sometimes you need to do that. So it's important to understand how they work so that you can do that. But even with the programs that don't allow you that kind of access, it's really important to understand how these assumptions are considered in the analysis, right? What assumptions are made and how important it is to get that whole picture from the beginning to the end of your analysis. So we're going to look at axial force systems, right? So specifically single axis and multiple axis axial force systems. A single axis axial force system is really just a spring or a bar, right? The two force members that we talked about before. And then we'll look at axial force systems that have multiple axes. So that's just a fancy way of saying truss, right? Versus something. So even though both truss members and single axis axial force systems we assume they only take axial forces, right? The difference is with a truss, because you have geometrically different alignments, right? So you have the axes are oriented in different angles. Then we have multiple axes, so we have to treat it a little bit differently. And then we'll look at beams, all right? So we've got single element and multiple element beams. And then later in the semester, we'll look at frames. Now, frames are essentially the combination of the previous two items, right? So we'll be adding essentially single axis axial force system behavior, which is axial only, together with beam behavior, where you have shear and flexure, right? So bending, moment, and shear. With a frame, you have to think about all of those. So we'll just say combine 1 and 2 for frames. You can also think of it as axial force system plus beam behavior gives you frame behavior. So now I'll go through a few definitions. First up, a node. This is essentially your point element with regard to finite element analysis. A node is a point of connection. It's also the same thing as a joint. We just tend to use the word node more in the context of finite element analysis. An element can be a line element or an area element. In this class, we're only going to be dealing with line elements in the context of finite element analysis. So we've got our line. So define as a line element, it is a member or a segment that is between two nodes. And then if you have an area, which is beyond the scope of this class for finite element analysis, but that would be an area member between more than two nodes. So then the combination of nodes and elements gives you the structural system. A degree of freedom, we abbreviate as DOF. This is defined as node movement tied to deformation. So it's important that we specify it's tied to deformation because as we'll see later on when we look at visual analysis, there are scenarios where a node could theoretically move in ways that the structure cannot, and so it's not tied to deformation. And the ways that a structure could move at a node that is tied to deformation could be, where we think of it as, three different categories. You've got two orthogonal directions, right? And then rotation. So continuing with this concept of degree of freedom, if we go back to the different types of systems here, an axial force system, if we just have a single axis that we're considering, that has 1 degree of freedom, right? So it can only move in one way that's associated with deformation, just axial deformation. With a truss, even though individual truss members are 1 degree of freedom because they can only deform axially, in terms of the total assembly of the structure, we have to define 2 degrees of freedom, 1 horizontal, 1 vertical, or so on, right? 2 orthogonal directions to represent the different, right, directions that any given truss element could move within the global XY Cartesian axes. And then beams are always 2 degrees of freedom. And frames are 3 degrees of freedom. Because we combine the behavior of axial force systems with beam behavior. So we have that single degree of freedom behavior of axial deformation combined with shear and moment for beam behavior gives us 3 degrees of freedom for frames. Now this is only for 2-dimensional problems. If we have a 3-dimensional consideration, a frame would have 6 degrees of freedom. So in this class, we'll just deal with 2 degrees of freedom. All right, so that should get you primed for finite element analysis. We'll continue on Wednesday.